My name's Aaron Morton, and today I want to talk to you about how to take Cassandra off your laptop and into the data center, and the types of mistakes that people make that mean they come and give me money, which I like, but sometimes I'd like to do some more enjoyable work. A little bit about myself before I start. I run a small consultancy called The Last Pickle. I've been using Cassandra for about 5 years. I'm a committer on the project, and we have staff around the world, and we just help people use Cassandra. So what we're going to do is we're going to look at the decisions we make at the design phase and the development phase and the deployment phase that mean that when we get to our cluster, it works. It always works on your laptop. I saw someone today with a sticker that said, "It worked on my laptop." We want to get it into the data center, and then we want it to work in the data center after 3 months and after 6 months, and even after 12 months. Let's start with the design choices we get to make. We're going to look at the data model. We're looking at it from the perspective of how to make data models that work at scale after 12 months. There'll be a lot of other courses that we've done today and yesterday and the day before around how to actually achieve functionality. This is about how to achieve performance and scale. So the first one we want to look at is we want to avoid doing unnecessary reads. We're going to do what we call no-look write. So say we've got a table that looks like this. We're just going to track the days that a user visited our website. Now, if you were doing this in an old-fashioned database, you might have a model like this. Read from it. If it doesn't exist, do an insert, so you add one. Which is a reasonable thing because you've got a primary key constraint in there. But in Cassandra, our primary keys don't have constraints on them. You can insert again and again and again with the same value. So don't bother doing the read. You're just wasting time and energy. Just insert it, and then let compaction take care of dealing with those overwrites. We've just cut out a bunch of disk I/O. Moving on, we talk about this a lot when we're doing data modeling, but we want to really limit the size of that partition in some way. Okay, I always use the phrase in space or time. So if we look at it when we're limiting something by time, imagine we've got our table of now and we're tracking every time the user visits, we record some piece of data. It's 100 Ks in size, for example. And we keep that forever. And so this table will grow, the partitions in this table will grow with no bound. And as long as your site keeps running, this partition keeps getting bigger, which means that we have more of a partition, we have a bigger index inside that partition that you don't even see and know about. It means that when it goes through compaction, it goes slower, because once things are above 32 megs, they have to go through a slower compaction process. And it means that when you do a repair, you are potentially copying around data that you don't need to, because we repair token ranges, not individual rows. If there's nothing wrong with this partition, except it's just next to a partition that does have an inconsistency in it, we'll copy this guy around. So if you've got a partition that's a 500 megs in size, we will just copy that to all the other nodes and then wait for compaction to do its thing again. So a better approach is to bucket. So we add another column on, and this time we're going to bucket up by day, and we put that into the partition key. And now every partition is only going to get written to for 1 day, and that means that it's not going to get too big. We have a fair idea of how big it's going to get. If you did the developer training, they went through a whole set of algorithms about how to work out how many bytes it's going to be. The simple thing you want to do to begin with is just, is there a bound on this? Like, how many times are people going to visit our website in a day? Something like that. Another issue we want to look at around tables is avoiding a mixed workload. So if you think about that log-structured merge tree storage engine, we can end up with fragmentation of your partition because we flush to disk and the rows get fragmented. And the job of compaction is to bring those back together. But compaction can only do so much. If you have a bad data model, you will have things spread out. And you can see how many SS tables your reads hit by looking at the SS table histogram, and we'll have a look at that later on. But the better idea, instead of detecting that you've done something wrong, is to not do it wrong to begin with. So imagine we had a table that looked like this. We've got the user's password and the last time they visit. Password gets updated frequently, read frequently. Last time they visit gets updated frequently, and let's just go with read infrequently. Two different workloads. It's going to create a table where it's very fragmented. And when we go to do the read path will have to look at all the fragments, even if you're just getting the password and that's only in one fragment. A better data model breaks up these two workloads into things that are updated frequently and things that are updated less frequently. And we'll see later on we could use that to use different compaction strategies in different areas as well. Level compaction strategy can be your friend. If you have a lot of overwrites, as we saw back here, we're updating the last visit time all the time. That's an overwrite. We want to compact away those fragments of that partition. Or if you've got a lot of tombstones, it can be your friend as well. It can be your friend if you want to do a lot of low latency reads. And it will be your enemy if you're trying to put too many writes through, because it uses about twice the disk I/O, and when it gets behind, it gets really behind and things get out of control. So LCS is good, but if you've got high write throughput, consider a date-tiered compaction strategy. And we add it just by adding a property onto the table. It's pretty simple. There are other properties, of course, of compaction. The level compaction strategy, you can say the size of the files, you can put settings in there about tombstone compactions and things like that. But the basic settings nowadays, the defaults are pretty good. This one's a little more complicated. So we want a data model that is going to scale the throughput when you scale your cluster. If you launch a site and you have 3 nodes and you're very, very successful and you get some money and you scale up to 30 nodes, you're going to have a lot more capacity in your cluster, but you also want to get more throughput out of that. So if we had a data model, let's say for hotel pricing, and we have the check-in day as the partition key, and then the hotel name and the pricing blob. Now, all of the check-in information to check in on the 4th of July is in one partition. That one partition is on 3 nodes. When you have a 3-node cluster, it's on 3 nodes, and when you have a 30-node cluster, it is on 3 nodes. You will not scale the throughput to read that. If you have a lot of people who want to check into a hotel on July 4th, you're not going to be able to successfully get all those requests out. So instead, we're going to put some kind of bucket in here. So let's break up the hotels by the city that they're in, have some other process that goes and works out which cities are near other cities so we know what cities we want to look at, and put that into the partition key so that now all the hotels in Santa Clara are on one set of nodes, and all the hotels in San Jose are on a different set of nodes. On a small scale cluster, on the 3-node cluster, they're all the same. When we move up to a 30-node cluster, they're spread out, and we can increase our throughput as we scale the cluster. And to do that, we're going to want to use asynchronous requests. So these came in, this is deep down in the native binary protocol. The native binary protocol is asynchronous by default. When you make a synchronous call through the drivers, it's just blocking for you. What this allows us to do is think in terms of paragraphs instead of sentences. If I want to go and get the hotel pricing information for 6 hotels, don't make 6 sequential requests. Make 6 concurrent requests using the asynchronous features of the drivers, and then wait on those 6 futures. It will be a little bit more than the network round trip for 1 request, but it will be significantly less than 6 network round trips. So back to our hotel model. This is our table. We go through our process to work out what cities we want to search, and then we send these asynchronous requests. And on the client side, I'm now joining it up. So I'm doing a scatter-gather approach. Client is now kind of an outer ring of the cluster. The driver understands where the data is, and it sends those requests out. And you scatter out those requests. They run in parallel. You bring it all back. You piece it together, and you get on with your life. Make sure when you're designing your data model, you document what sort of consistency levels you expect people to be using. Because often the people making the data model and the developers are the same people to begin with, and then there's some new developers that come along and they don't really understand why, or they just have to copy what's in the code. If you write it down in your data model, you can explain why you think you can use eventual consistency in this area of the application. It only has to be a couple of sentences in the schema, that's all. And then smoke test your data model. The idea of the smoke test is to find problems as early in the process as we can. So we may insert, for our hotel data, have a little script that inserts some hotel prices and the cities and their relationships to each other. And then all I do is I write a couple of select statements, and I put some comments in the schema, in the script, and I say, run these in parallel, make this before that. And I can test my logic. I can make sure I understand that, yeah, I can read from that table, get a value, and write it to that table. And it's a great communication tool. So once we've gone through the design phase, we're going to move on to development. So we're not going to get into too much dev detail. Again, we're just looking for the best practices to avoid problems 12 months down the line. First one is we want to understand how much we're reading from Cassandra. So it may be that you're reading cells, columns, that have 20 megabytes in them. And the thing to do would be to not put 20 megabytes in one column. Or it may be that you're reading tens of thousands of rows. The important part is to know what you're reading, how much you're reading back. So again, in the native binary protocol, at the base level, there is support for pagination. Whether you see it or not, it's there and is always enabled. The driver sets this by default to be 5,000 rows. So if you do a select against a partition, and it has 5,000 rows in it or more, you will get multiple pages come back. This is called the fetch size. 5,000 might be a bit much if you've got a bunch of data in there. If you've got some large rows, that could be quite a significant amount of data. So you might want to turn that down to be 100, 200, whatever. Also, so in the background, the driver is going to fetch again. And it will either, by default, it does it synchronously. So you exhaust the iterator, it goes back and gets the next page. Or you can make it do it eagerly. So once you start reading from the iterator in the background, it goes out and gets the next page and brings it back. Again, we're going to use the appropriate consistency level because reducing to the lowest consistency level improves performance, improves throughput. And we want to, wherever we can, use token-aware asynchronous requests at consistency level 1. So we touched on this before in the design phase. What this means is your client is paying attention to the tokens that are assigned in the cluster. And when it's going to write or read a value, it works out which nodes are actually replicas for that. Directs the request to one of those nodes. And if you're using consistency level of 1, it can answer that query using local disk only. It will still do, if it's a write, it will still send it to all of the other nodes in the cluster that are replicas. And if it's a read, it may do some reading in the background to check for consistency and repair it, but you've taken network latency out of it. You've taken one network hop out of the picture, and it can really reduce your latency down. So you set this up using what are now like lots and lots of policies and properties on the driver. You create your cluster, and in this example here, we create a DC round robin load balancer. So it's going to, the internal policy is going to round robin across all of the nodes that are replicas, across all of the nodes, in DC1. And then the token aware policy wraps that and filters them down so it's only the nodes that are replicas for that partition. And if we want to do asynchronous requests, we go to our session object and we call execute async, and it gives us back a result set future that we can listen on using Guava, or we could call get interrupt uninterruptedly if we want to. It's pretty simple stuff. It's just going to give us the row back. Now, if you're doing this, you really should avoid doing a denial of service attack on your cluster. Okay, so your client is probably running at the speed of memory. It's just got stuff coming in, and you just want to send it to the cluster. Your cluster is running at the speed of disk. If you just send a lot of asynchronous requests and don't wait for them, there is a pretty good chance you may overload your cluster. So if you want to send like 1,000 writes, maybe only have 100 of those in flight at any time. Again, the number's not so important as the fact that you think about it and make sure that you don't have it set up that if your site gets really busy, you didn't have any protections in place, and the amount of writes that were in flight on the cluster went sky high. I think that monitoring and alerting is part of development. That if the developers have access to monitoring early on, they can see how their system is running or not running. And that most developers should be writing metrics that that you want to see on the graph with the metrics that you see from Cassandra. So you can understand latency going through your stack, that kind of thing. Now, you should just use whatever works. Ops Center is getting better and better. Riemann is very good, but very complicated. Grafana looks nice. LogStash does lots of funky things. Sensu has lots of functions, but it's a bit complicated. Whatever it is that works, get it in and work out how to get as many metrics as you can out of Cassandra and into that system as early as possible. When we're pulling these metrics in, we're going to want to do some aggregations. Remember, they're going to be coming in off one node, but if you've got a 50-node cluster, you have to think about what's happening at the cluster level, what's happening at the node level. So we generally want to have some aggregations at cluster-wide. We want to know throughput across the whole cluster. If you've got a smallish cluster, you may be able to show the value for every node on the same chart. It's often useful to have a filter that pulls out the top 3 and the bottom 3. If you've got some nodes that are processing more writes than others, you may have a hotspot in your data model. And that will become evident if you filter on top 3 and bottom 3. And then you're going to want to be able to drill down onto individual nodes to see what they're doing. And the type of metrics that we get out of Cassandra are a 1-minute rate, which is an exponentially decaying average of the throughput every second. So the throughputs for the more recent seconds have a greater weighting than the older seconds in that minute. And sometimes we have just values that are counts, and you're going to want to run a derivative on that to get the delta over time. And then we have lots of latency metrics, and they come out with a min and a max and a medium and a standard deviation and things like that. I tend to just grab the 75th, 95th, and 99th percentile for those, and these things report in microseconds. Whichever process you go to get your metrics out, they have a naming scheme that is reasonably consistent. You can get your metrics via JMX. You could use Jocular or MXML to get that via HTTP. You could have collectD pulling things off, or you could use, I think the preferred method is to use the configuration file called mymetrics.yaml and configure Cassandra to push metrics out to the reporting systems, which is much better approach. You can configure it to push to multiple reporting systems. You can configure it to push at different intervals to different reporting systems. You can have regular expressions that are going to filter the metrics that are shown. It's a really useful thing. So they have a naming scheme that starts with org Apache Cassandra metrics, OACM, and then we get into the different areas. So we have one here for the cluster throughput. This is an aggregate of the throughput on this node, and we have the write latency, 1 minute. The latency bit is a little confusing. This is the throughput, this is not the latency. We'll see the latency in a few minutes, but that's where the throughput hides in the client requests. And then we have the throughput for the node. Now, if we've got a schema that has RF3, the throughput to the cluster, and we'll say is 100, the local throughput should be around 300 because we're going to do 3 writes for every request that comes in. So you can see the throughput at the individual column family level, and it's org Apache Cassandra metrics, column family, then your key space name, then your table name, and then write latency again, 1 minute rate. And we can see the request latency. So the timer for this starts when the request hits the coordinator from your client, and it ends when we send the response back. So it includes all of the wait time, all of the internal network traffic, all of the disk access, all of the queue times, everything's in there. It is the most important number to understand, I think. Everything else, like a bad data model, if you've got metrics telling you that your data model is bad, but your SLA is being met, then you probably shouldn't spend too much time trying to fix your data model. There's probably more important things to do. So we have that request latency, but this one is for all the requests coming through the cluster, through this particular node, and then it can be broken down by individual tables. So you go OACM, column family, your key space name, your table name, and down here it's called coordinator write latency and coordinator read latency. This is really important because you might look at that one number to begin with and see that the 95th percentile is 1 second, but you don't know what table it is. So you can drill down here and see that, oh, it's table foo is the one that's where the 95th is 1 second. The next level down on latency is the local latency. So this is what's happening when that read thread gets the message off the queue on each node and starts pulling information off disk. And this is telling us how fast this particular part is running. So for example, write latency might be about 50 to 150 microseconds, and read latency might be around 100 to sort of 800 microseconds. And once you start to look at these numbers, you get a feel for what that network latency is all about, because that number is typically a lot smaller than the overall request latency. Now, most problems that people have are to do with the read path. And there are 3 key metrics that you can look at to understand the read path. The first one is the live scanned histogram. Now, I've just pulled out the 95th percentile here. This is how many cells, which is an internal representation of a non-primary key column, how many cells we read per read, and breaks it down for the percentiles. So you could look at this and understand if you're doing huge reads on this table. Maybe that's why the reads on it are kind of slow. And we've got the tombstone scanned histogram. And this is how many tombstones we've read off disk. And remember, those tombstones get read off disk, allocated memory, and then thrown away. So we don't want too many of those around. Again, this is a histogram of per reads. And then we've got the number of SS tables that we touch per read. And this goes back to the fragmentation that we talked about earlier on. The more SS tables that we touch, the slower the read, because there's more random disk I/O in there. Now, things go wrong, and then we get into eventual consistency, and everyone wants to know how eventual is eventual, and nobody knows. It's totally non-deterministic, but we can get a bit of an idea about how many times things are going wrong. So we have some metrics that let us know how many hints we've stored, storage.total hints. It's a count, you have to do a derivative on it, but you can know how many hints you've stored. And remember, the hints are when a node was down before we started the request, or when a node timed out, didn't get back to us for a write. And then it's broken down per IP address. So you're going to know that, oh, look, the nodes on the other side of the WAN are the ones that we're storing all the hints for. But don't forget that hints are an optimization. They can be turned off. And by default, if a node is down for more than 3 hours, we stop storing hints for it. So there's another measure here, which is timeouts. And this is the rate of timeouts that you're getting talking to other nodes. And it's a good measure of kind of your network health and lets you understand if you've got problems going across the WAN and things like that. On the other side of this, we have to repair it. So we've got read repair. There is read repair that happens in the background and doesn't slow anyone down. As read repair background, we could know how many times that detected a problem. And we've also got read repair that's blocking. This is where you do a read at a consistency level that's higher than 1, and the coordinator checked the 2 results that it got and decided that they didn't match. And it has to go and fix that while the client's waiting. And so that's the blocking read repair metric. Occasionally there are errors. We know there are 2 types that happen in Cassandra. And the first one is the good one. Unavailable exception says, you asked me to do this read or this write at a certain consistency level, and I can't because there is not enough nodes available, so I haven't even tried to do it. The second one is the bad one. Timeouts are essentially, we just shrug our shoulders and we don't know what happened. Both of these should be tracked and alerted on and measured. And if you're managing the system, it feels good if you know about the problems before the developers come and annoy you because they're saying there are errors in their logs. There is also errors that Cassandra has, not many nowadays, but there can be errors. And there is an unhandled exception handler that will catch those. And that's tracked here. You'll also see this if you do no tool info. It says how many unhandled exceptions. It's normally 0 nowadays, but it's handy to know if there's something going on. You might want to understand how much disk you're using. So there is Apache Cassandra metrics storage load.count. And then you can get that's the number of bytes, and then you can get that per table as well. So you can understand which tables are taking up the most space. Speaking of taking up space, there is compaction, whose job is to squish down all of our overwrites and tombstones and make things take up less space. There are metrics that tell you at the grand level how many pending compactions there are. There are metrics that tell you how many pending compactions there are per table. And there are metrics that tell you how many you've completed. So you might want to alert on this if your count of metrics gets above 50 or 100 or something like that. You're not looking at this stage for poor performance, you're more looking for abnormal performance. Like, have we suddenly got a problem that compaction isn't working and now we've just gone off the charts? And if you can catch that at the compaction level, you may catch that before it impacts your read latency. Now, inside Cassandra, there are a number of thread pools, and your requests journey through these thread pools. We won't go into them all, but they generally do the type of thing you'd expect from what the name is. So there's a mutation stage that does mutations, that does writes, and a read stage, and replicate on write is for counters and things like that. It's a queue with a number of threads at the end of it. And the pending says how big that queue is. Often it might be 0. You might get a large number of requests come in, and it might take a split second for it to get back to 0. So you can monitor this, and it's a good indicator of how up to date the cluster is. Now, if those messages sit in the queue for too long, they get dropped. It's part of the load shedding process that Cassandra has. How long they have to sit there for is controlled by the timeouts that you have in the YAML file. And so by default now for reads, it's 5 seconds, and for writes, it's 2 seconds. If we are dropping messages, then we are shedding load. It means the cluster is overloaded, and we want to track that and know that it's happening. Could be an early indicator of something going wrong. Important thing to remember is that we can drop messages and shed load, and the system can still be functioning correctly. So long as we go back to the client and say, we successfully processed your request at the consistency level that you asked us to, we're good. If we drop messages on one node, that's fine. All right, so now we're up to provisioning, getting a system out and running. I mentioned smoke tests earlier on, around smoke testing your data model to kind of check your logic. You can go and smoke test your disk. which is a good thing to do, and Toby has a good write-up about how to do this and the types of numbers that you'd expect and the techniques that you can use. Just make sure that the disks are not broken before you go and start to use them. You can use the Cassandra stress tool and just run a smoke test. Just stand up your cluster and run this beforehand, and if it has any issues, you can fix them before you go to all the trouble of getting your application provisioned and everything else. And there's a blog post on DataStax about that as well. And then we start to build runbooks. And the idea of the runbook is to plan how you're going to handle some bad situation in the future. And my goal with a runbook is always to communicate like a 10-year-old. Like, I did this because of this. On the weekend, I went to the park, type of stuff. And explain what we're doing and how we're doing it and why. And the way you test your runbooks is you run fire drills. And then the fire drill is to see that the runbook works and that people understand it. And if you're in a fortunate position that you're deploying a new system, hopefully you can do this early on. So here are the scenarios that you want to run through. First one, I call it a short-term node failure. The node is down for less than the hinted handoff window, which is 3 hours. So the other nodes collect hints for it. We continue to be available for quorum requests. And at the end of it, there's no action necessary, because this is what Cassandra is designed to handle all the time. But you want to test it. You want to make sure your application's happy. The next thing we want to do is break the cluster. Like, take down multiple nodes until the cluster breaks and hopefully understand how the application reacts in that situation. And if you care about this in a runbook situation, you should run a repair when you come back. Then we can maybe lose an entire availability zone or a rack or something like that. So we could put in some IP tables or shut the nodes down or whatever we want to do for that. And we should still be available for quorum if we've designed it correctly. And that would be a good test. It would test your application as well. And when we come back, we may want to put repair in to make sure that all that data gets back. We could rely on hints, but if you've got a high throughput, it might be faster to run repairs. The next type of failure I call a medium-term failure. So that's where we're down for longer than the hinted handoff window, and we can't rely on hints anymore, but we're down for less than the GC gray seconds, which is important. We'll see that on the next one. So this might be the case where you've disabled hints because you don't need them, or you had a failure overnight, and you woke up, or you didn't even bother waking up, and you're going to fix it 8 hours later. So it's a fairly common scenario. You should bring it back and run repair, because it will have missed a significant number of writes, and hinted handoff will no longer be storing those writes and replaying them. And we've got long-term failure. This is where a node's down for more than the GC gray seconds, which means that any tombstones and TTLs that were created may now have been purged off disk, and the node that was down may miss the deletions, and data will come back to life. And you should never bring this node back into the cluster. You have to replace it. Delete all the data and start the node with a dash replace node. And if you look at the DataStax docs, it explains how to bring back a failed node in that state. Now, with all that practice in place, you can understand now what happens in a rolling upgrade. It's just repeated short-term failures. So you might want to, in a fire drill, do an upgrade. Sometimes it's good if you're provisioning, provision the revision before the revision you want to run. So if you want to run 2.19, provision 2.18, put the application in, run some load tests through it, and then do an upgrade to 2.19 while it's running. And if you want to scale up, where you just want to lift up all the data and config from a node and put it onto another one, again, that's just short-term failure. And what you want to do is make that failure mode while it's turned off as short as possible. And if you're going to scale out, you're not going to have any impact, so you're going to scale out and you'll be available for all. And again, if you really want to get into this, you can provision your initial system with not all of your nodes. If you're going to go to 6 nodes initially, provision 5 of them, put the application in, run it, and then while it's running, add another one. And get some confidence that that's going to happen. So that's all I have for today, and I've got about 5 minutes if there are any questions. No? Yeah, question down the front? Sorry.
Hi, were you going to be getting into anything discussing chef recipes?
Am I going to get into anything about chef recipes? I thought I might be able to, but I didn't quite have time. I really like having your config be consistent is a great thing. Making sure that your automation doesn't go crazy is another great thing. So I just ran out of time in today's. Yep. Some questions there?
Thanks for the talk. Do you have any operational experience with different types of rating, either RAID 0, RAID 10, JBOD, and what you're feeling on those types?
Yeah, so question is about using different disk layouts, or RAID and things. I've worked with enterprises where they say the box is a RAID 10 and it has 20 disks in it, and that's the only box we have, and that's fine. The biggest concern you have is if a disk fails, how long does it take for the disk to get replaced? So if the gardening happens once a month or once a week, how long will it take to get replaced? In terms of performance, it's JBOD is pretty good, and RAID 0 is pretty good. The problem with RAID 0 is if you lose a disk, you lose all of the data. So generally nowadays people go for JBOD. It can be a bit of a pain with fragmentation on there. So I would go with like the best hardware accelerated RAID, and if you don't have any, I would just use JBOD.
Do you have any recommendations on how to identify hotspots in your nodes?
So to identify hotspots in your data model, you want to look at the local write throughputs, and you want to find the top 3 and the bottom 3 per node. Like so, for your table, across all nodes, get a line for each throughput. And if you see one that's getting more writes, then that's a hotspot there that's getting more writes, and same for reads. Understanding that you've got fat rows, you can use NodeTool CF histograms and NodeTool CF stats, and it will tell you if there's what the biggest fragment is. And if that's a lot bigger than your average, then you've got a hotspot somewhere. Then finding that in the data model can be hard.
Okay, thank you.
Cool. There's a question at the back there.
Do you have an opinion on or experience with join ring false and repairing in the case that the node has been down longer than the hint storage window?
So the question is about bringing a node back that's been down longer than GC Grace and join ring false. Yeah, so join ring false is what we used to do, but now there's an option called replace node, which either takes the IP or the host UUID of the node you're replacing. The node joins the ring in a joining mode. It accepts writes from the other nodes. It doesn't accept any reads from the other nodes. They don't send any to it. It initiates a streaming process, and so it's accepting writes and streaming all the old data, and once that's complete, it then joins the ring. So it's a better model. There's a much smaller gap for eventual consistency to creep in. Cool. Oh, one last question, thanks.
So my question is about repairing nodes. What I have sometimes observed is that if a node goes down, the coordinator who is storing his hints sometimes also gets down or very busy. So in those situations, what's the recommendation? Should I just bring down both the nodes and repair both of them? So what's your take on it?
Sorry, I didn't catch the bit in the middle. The fans are a bit noisy there.
Okay. So what I'm saying is that when a node is down, generally the coordinator who's storing his hints sometimes also gets very busy in a very write-heavy traffic, and also goes down or becomes very slow. So in such situations, just to bring back the cluster in a healthy state? Should I kill those both nodes and bring back both, or what should be the...
Yeah, so the question is about when hinted handoff goes crazy. So in the situation where the node goes down and the nodes that are storing hints go down as well, you bring them all back at any time. It doesn't matter which order you bring them back. And if you're in a situation where you, once you lose a node, you can't handle the throughput, it sounds like your cluster needs to grow. So remember, you're doing n+1. You should be able to handle all of your throughput and latency on n, and the +1 is the extra. So you may need to grow that cluster. Cool. Okay, thanks everyone.